So problem number 2 says that a force of F equals 240 newtons is applied as shown to a bracket ABC. Determine the perpendicular distance from point A to the line of action of the force. All right, so let's break this down. So I wrote out our givens, which is the force, as well as I denoted A as our origin. So let me draw that out like this. So this is our origin point. And I from A, C is equal to 60,750 millimeters, which is also equal by moving the decimal place over 3 times to the left. We can get it in meters, which gives us 0.06 and 0.075, and then 0 meters. All right. And so we want that in meters so that the units can work out well with the newtons because the SI unit is in meters. And then notice in the problem that it's also saying to the line of action. So it's not saying that, if you remember, the line of action of a force can be drawn out um, at any length parallel to that force. So the line of action looks something like that. And so what we want is from A, we want this perpendicular distance coming out of the page, touching the line of action like this. And then this denotes that it's a right angle or a perpendicular distance. So this is this green line that we see right here is the distance that we're looking for, the perpendicular distance. And so let's go ahead and start doing our analysis. So first, we have that F is equal to 240 newtons. We can break that up into its vector components by using cosine and sine identities because we're given the angle in the problem. And so we know that F is going to be equal to negative 240 cosine of 30J plus 240 sine of 30 degrees K. And that makes sense because if we look at this 30 degrees right here, the adjacent side of it is pointing downwards in the negative y direction, and its opposite component is pointing in the positive z direction, and it has no x component. So we've broken up our force component, and now we want our direction vector pointing from A to C. So I'll draw that out right here. And the reason that I wrote down the coordinates in the beginning of the problem is because we can do the final minus initial to find the direction vector of RAC. So we just subtract C from A. So we also know that RA of C is equal to 0.06 I plus 0.075 J. And that is in meters. Okay. So now, with that information, we can use our moment equation using a cross product to find the moment about A. So let's set that up. We have the vector moment about A is equal to R A of C cross F, which is equal to, and then I'm going to set up this cross product like so with our I, J, and K component. And then remember the order of the cross product matters. So first has to be the direction vector. So I'll have 0.06 under I, and 0.075 under J, and 0 under K. And then our force is going to be 0 under I, negative 240 cosine 30 under J. And then let me move this over a little bit. And then 240 sine of 30 under K. All right, and so now solving out this cross product, remember that we cover up the first column in the first row. We multiply these two entries, subtracted with these two entries. Because there's a 0 here, this basically cancels out. So our I component is just going to be the multiplication of these two entries. And then you can do the same for J and the same for K. And when you do the entries for the J component, there's a negative sign in front. So I'll write that out. So we have our moment is equal to 240 times and then 0.05 sine of 30 degrees I, and then minus 0.06 sine of 30 J, minus 0.06 cosine of 30 K. All right, so that's the component of our moment. Multiplying out the 240 newtons that we have right here, we would get, I'll write it down right here, we'll get 9I plus, or really minus 7.2 J minus 12.4708 K. All right, so that is the component of our moment about A. There's a moment being applied in the X direction, the Y direction, and the Z direction. But remember, this equation right here will give us the about the perpendicular distance. So now what we want to do is get our moment from a vector form to a scalar form. And what we can do to do that is take the magnitude of the moment about A. So we'll take the magnitude, and that's equal to the square root of all the entries squared. So we'll do 9 squared, and then the sign doesn't matter because they're being squared, so you can just add them all up. So 9 squared plus 7.2 squared plus 12.4708 squared. And that will give you that the magnitude is equal to 16.9812 Newton meters. And sorry, I forgot my units right here. It's always a good practice to write out your units. So that was my mistake. And then now that we have our magnitude, we can rearrange the equation and solve for the perpendicular, which is equal to the magnitude of the moment about A over the force that we were given, also its magnitude. And so we have 16.9812 Newton meters all over 240 newtons. And that, when you plug into your calculator, will be equal to 0.0708 meters. And if you want to change it back into millimeters, you can move the decimal place over to the right 3 times. So you have 70.8 millimeters. And that is the final answer.